We're now going to take a look at solving relatively simple exponential equations. I'm using two different methods, one by equating the bases and another one by using what we just learned, those logarithms. For the first method, equating the bases, you're going to need to be very, very, very comfortable with those exponent laws because it doesn't always jump out as what might be the easiest way to do it. These first two I have are relatively simple. Two, like that would be a great direction to go with the base here. Here, you could either use 2 or 4. It doesn't really matter either way in this particular case, but you'll see in the next one that you need to be comfortable kind of trying around if they get more complicated. So first off, I will use 4 in this particular case. You can always go down to smaller numbers if you like. And you need to be able to recognize that this is 4 to the negative third. So 1 the reciprocal to make it the fraction that you see, and 4 to the third. So this is 4 to the negative 3. And by doing this, what I see is 4 to the something equals 4 to the something. Then those things must be the same. So you can really just get rid of those and say, okay, x plus 2 has to then be negative 3. Otherwise, it's not possible to be true. So x is negative 5. Here you have the same idea. This is pretty close to being already in the same base. So that's a 2 to the x equals, this is 2 to the negative 1. This is 2 to the half. Gonna need some exponent laws here. I'm gonna add those two exponents. Negative 1 plus a half is a negative half. I'm gonna write it like that. And again, what you'll see is if I equate the exponents, because 2 to the something equals 2 to the something, x is negative a half. So it can be quite simple. Again, assuming you're comfortable with those exponent laws. But you may also get something like this, where it's really not as clear. Something that kind of jumps out to me as I'm looking at this is like 2s and 3s. 2s go into both sides in a nice way. We may have to do some division along the way. In this particular case, we don't, but it is possible you may need to move stuff around to get to something where you have something to an exponent equals that same thing to another exponent. And what I have here is I'm going to go down to 2s and 3s. And you may just need to keep trying things until something jumps out at you. This is 2 squared to the x. It's not a great x. I'll fix it in the next one. This is going to stay the same because I'm working to 2s and 3s. This, I'm going to go somewhat slowly here. 1 over... That's going to be, how about I get to 6's first, just to take it step by step. 6 squared to the x. Hopefully I won't need more paper. Times 6. It might be more clear already where we're going. Maybe I can write a little bit thinner. To the x plus 3. Oh, this is a times. Oh, that wouldn't have been possible. Don't do what I do. Please make sure that your stuff is very clear. I may have to switch from this black marker. It seems to be getting a little bit chunkier every time. And that's going to be a problem because neatness is very important. Okay, and I forgot the square root. Look at me go. Taking the square root of this, you can think of it in any number of ways. All of these exponents are in the same order of operation. So this square root you can cancel out with the square. Okay. You could multiply all these out first and say to the half, and then I'm going to cancel things out. But we've done exponent laws, and if you're not entirely comfortable with them, then do come talk to me, and we can talk about the longer step of seeing where that is, hopefully without me making all these little mistakes along the way. And what this is going to be is I have 1 over 6 to the x to the negative 3 times 6. And actually, this is looking pretty good to make it a 6 because that's 2 to the 2x times 3 to the 2x. I'm going to flip this over and make it positive. Okay, remember that will say take the reciprocal. And once I take the reciprocal of this, I can make it positive. I don't want to keep the negative once I've applied the negative in that sense, though. Times 6. And this is not really a straight rule of you just do this, this, and another thing. You have to play around a little bit to see where it might go. These have the same exponents now. So again, thinking of that other power law product rule with the exponents, this is 2 times 3 to the 2x. And this is 6 to the 3x times another 6. So 6 to the 3x plus 1. That's all the exponent. This is 6. How would I make that more clear? I think this is an invisible 1. This is a 6. And now I have 6 to the 2x equals 6 to the 3x plus 1. So 2x equals 3x plus 1. And just because I'm running out of space, I'll go over here. So if I subtract the negative 3x, so I have negative x equals positive 1 or x equals negative 1. Okay. But that's just sometimes a matter of playing around and getting really comfortable doing these and seeing what jumps out at you might work. And of course, not making the mistakes I did, because that will lead you a little bit away. You can also use logarithms. I could put this and say, well, 2 to the x equals 2 to the 4th, and then x equals 4. But another strategy is using those logarithms that we talked about before and rearranging. If you remember the format, I'm not going to color code it here. You do have it in your formula booklet. If you have some exponential equation in this form, you can convert it to the logarithmic form, log base a of b. We always solve for the whole exponent. And there it is. Okay, so I can really easily convert that and say, okay, well, I'm solving for my exponent equals log base 2 of 16. In this particular case, it's not entirely helpful. It's probably more natural to even think, well, that must be 4. But you could put this into your calculator if the numbers weren't so nice. You can put in log base 2 of 16, and it would say, well, x equals 4. Okay. If you have something like this, do recognize, again, logarithms solve for the exponent. There's nothing else going on around it. So I'm just going to jump right in and say, okay, I'm already down to the point where I have to solve for my exponent. And again, knowing what this is kind of doing, we know that 3 to the 4th is 81. So I know that this wants to be 4. But if the numbers weren't as nice, I could put this into the calculator and get this. And then, of course, I want to solve for x. Logarithms solve for the exponent. They don't necessarily solve for x. Add 7 to both sides and I get 11. You could, however, have something a little bit more complicated, like this, where there's more going on. And it could be any number of things. But what you want to remember is, again, as always, the order of operations, PEMDAS. And what we're going to do is as we simplify, we work down, right? Going back to the order of operations, we do what's in parentheses first, then exponents, all of that. That's for simplifying. And when we're solving, we're going to go back up. So I first want to work outside of parentheses. Some people call this a G for groups because we don't necessarily need visible parentheses. This is GEMDAS. This is a group. It's stuck inside. I can't get to it yet. There's no addition or subtraction outside of the exponent that I can get to, so I don't want to undo that. But there is multiplication. And the first thing I want to do then is I need to undo that times 3. I'm not even at the exponent yet. And to undo times 3, I need to divide by 3. E to the 1.7x plus 4 equals 123 divided by 3, which is 41. Okay. Now I'm inside the exponent. Remember, if we know what the exponent is and not the base, we can use roots. And if we know what the base is and not the exponent, we want to log. And that's our situation now. So I'm going to take a log base e of this, and it will give you our exponent. Log base e, we write as this, ln, the natural logarithm, because this is talking about natural growth of 41. It includes the base. We don't then write the e. Could put this into my calculator. It's not going to be a nice number. This is an irrational number anyway, so I'm just going to leave it like this. It depends on the type of problem, whether you'd want to give an approximate answer or a rounded answer or leaving it this way. And if it's a word problem, for example, how many people, of course, you wouldn't probably want to leave it like that or even with decimals. But for now, this is absolutely fine. And that's breaking into this group, my invisible parentheses. And then I get to start over again. So I'm going to undo any addition and subtraction. I'm going to subtract the 4, 1.7x still equals ln 41 minus 4. This is one thing. It's not 41 minus 4. Order of operations would say I do this if I'm simplifying, and then that, not this. And then to get x by itself, divide by 1.7. Those are my lines. I can make them a little bit more clear. So ln 41 minus 4 all over 1.7. This could be put into your calculator. This is a true answer. It is absolutely fine unless the problem is saying give an approximate answer or it's not a reasonable thing to give. And that is that.